Okay, what I'd like to discuss now is the concept of the vector cross product. I've snagged 4 images out of the Hibbler text, and the first one up here in the upper left-hand corner is showing a general vector A being crossed into vector B, producing a vector C. So the C vector is equal to A cross B. Now, if we take these same exact vectors B and A, and I cross B into A, I get a vector C that is in the opposite sense to vector C over here. All right, well, what's happening here becomes a little bit more clear if we look at it in a Cartesian coordinate system. So we have our standard X, Y, Z coordinate axes, and along with these, we have the 3 unit vectors I, J, and K. Well, we can define K as the cross product between vector I and J. Now, using the right-hand rule, and the reason why they're showing the hand here, is that if you take the fingers of your right hand and direct them along the positive x-axis and curl the fingers towards the y-axis, your thumb will point in the direction of K. So, and that is how you're doing the cross product. In a more practical sense, you can see that the vector I directly crosses vector J. And because they cross at a 90-degree angle, it is then the magnitude of I and the magnitude of J are equal to the value K. In this case, 1 times 1 is 1, and the direction of the vector that they produce is perpendicular to that plane formed by I and J. All right, we'll get a little bit more into it, but now for the sense of how we do this, we take vector I, J, K, and as long as we're rotating along this circle here in the counterclockwise direction, they'll be positive. So we have I crosses into J, produces K. J crossed into K produces I, and K crossed into I produces J. If we were to do it in the opposite direction, say you have a vector I that you're going to cross into the unit vector K, you'll end up with a negative J, and so on. Well, let's take a look at a couple examples here. So in this case, we have a block, and we have a point O, which is where we're interested in calculating this thing called a moment. And how we're going to define the moment is that there is a force vector F, which in this case is pointing in the positive x direction, and we look at its point of application. And this, it's a physical point on this block that the force vector is being applied to. Now, what we're going to say here is if we follow, or we took the fingers of our right hand and put them and directed them along the r vector, in the direction of the r vector, and crossed our fingers into F, we would get the direction of the moment. So here's the vector r, here's the vector F, and if you took your, as I said, if you take the fingers of your right hand, point them in the direction of the red vector, cross your fingers into the F vector, you'll find out that your thumb is pointing downward, in this case in the negative z direction. And we're going to say that this force vector at the distance r, so again r is the perpendicular distance from the force vector, from the line of action of the force to the point of rotation, it's going to cause in general a rotation in this direction, which would be what we're going to call negative, and it'll have a value of the moment about point O. Okay, well, we can formalize this again if we take our r vector, our f vector, them being crossed together produce a vector that's rotating in that direction, and we'll denote it as the moment about point 0. So here's the mathematics of it over here. There should be a bar above this r vector, but the moment about O equals r cross f. Now we can see that r is pointing in the positive y direction. Right? We see our x, y, z triad up here, and f is pointing in the positive x direction. So we have r, j cross fi. Now what we can do is, for this type of cross product multiplication, we're going to take the scalar components out and multiply them together, and then that leaves us the cross product of unit vector j crossed with the unit vector I. Now again, the product of this is 1 times 1 is going to be 1. We're just looking for the direction vector. Now I come down here and I looked at j crossed into I, but I'm in the going in the clockwise direction, so it's going to have a negative value, a negative k. So we find out that the moment about point O has a magnitude of RF, and it's in the negative k direction. Of course, I can write it that way, with negative RFK being the way you'd probably typically see it represented. All right, let's take a look at another example. In this case, we have R is pointing in the negative y direction, F is pointing in the positive x direction. So this is, again, if we think about what's happening, the vector f is going to try to rotate this entire block about point O in a direction, and that's going to be the sense of rotation, and we're going to again call that the moment about point O. And let's take a look at how the cross product is actually constructed. So the r vector is pointing in the negative j direction, the f vector is pointing in the positive I direction. So in this case, I can actually bring the negative sign out with me to allow me to calculate my cross product a little bit easier. So I have a negative RF. Now we do J cross I. So again, J cross I is again going to give me a negative K. But now I have a negative sign here and a negative sign here. They cancel each other out, and we end up with a positive direction. So again, if you take the thumb of your right hand and you point it along the positive z-axis in the direction of this moment arrow, your fingers will curl in the direction of rotation. And again, if you physically think about this, if this was literally an axis going through point O and you pulled on the block with a force vector located at along the line of action of F, this block would rotate in this direction shown by the purple arrow. Okay, looking at another example, we now have the r vector is pointing, oh, sorry, we're doing the f vector first. So the f vector is pointing in the negative j direction, and the r vector is in the negative x direction. Again, you can think of the sense of rotation right now, and without even doing any calculation, you could see that if you take the thumb of your right hand and point in the positive z direction and curl your fingers, your vector would end up looking like that. And there's the sense of rotation. And we can again denote this as the moment about point O. Again, looking at the mathematics here, we now have R times a negative I crossed with F times a negative J. So our negatives are going to propagate out with our scalar values of R and F, and we're left with an I cross J. So our I cross J, now we're rotating in the counterclockwise direction, so I cross J is going to produce a K. And indeed, that's what we're finding. If we take the moment is pointing such that I take the thumb of my right hand and direct it along the positive Z direction, and the curl of my fingers is going to show the general rotation of what this block would do. Now, we don't always have to have rotation around the z-axis. In this particular case, I have the r vectors pointing in the negative y direction, and the f vector is pointing in the negative z direction. So the sense of rotation now is going to be about the x-axis, and it's going to be along the positive x-axis. I don't have a nice little arrow here because I couldn't find a good graphic, but the rotation is in this direction. So again, taking the thumb of your finger of your right hand, pointing along the positive x-axis and curling in the sense of rotation. So we come up here and take a look at the math. We have R is negative J, F is negative K. So again, I'm going to propagate my negative signs out. So I have an RF. Now it's J cross K. So J crossed into K. Again, it's going to be a positive direction. So J crosses into K to give me a positive I. And that is what I'm expecting again, because I'm expecting a positive, the moment vector points in the positive I direction or in the positive X direction. Okay, a last one here now. We have the R vector is pointing in the positive X direction, and the F vector is pointing in the negative Z direction. So we can almost see here that this is going to cause rotation about the Y axis. And now notice point O is in this back corner of this block. and we're pointing in this direction. And that's moment about 0.0. So again, looking at the mathematics here, we have an R in Ri f negative k. So we can take the negative sign and my RF scalar out, and I have an I cross a k. So I cross with k, I'm rotating in the clockwise direction on this unit circle over here, so this is going to give me a negative j. So I have a negative and a negative. They'll cancel each other out, and we end up with a positive RFJ. And again, the moment vector as shown in the figure here is pointing in the positive y direction. All right, so that's it for our discussion of what the cross product is. The next video will discuss how we actually calculate the cross product.